Hello and welcome. In this video, we want to take a look at an example of a double integral where we're going to use a change of variables substitution to solve the integral. And it's not going to be polar coordinates, it's just a different substitution. And I'll have to use the Jacobian. So here's the example. It's just the double integral over the region R shown here as this tilted rectangle. Simple function, x plus y, are easy enough to integrate. But the region here, drawn as this rectangle, it's the region that's bounded by the lines y equals 5 minus 2x, that's this one, y equals 12.5 minus 2x, that's this side over here, y equals a half x, that's this bottom one here, and y equals 2.5 plus a half x is this one up here. Okay. Now, you might think, why would I bother to do a substitution? This is really easy to integrate. And I will admit that it is possible to do this without doing the substitution. But look what happens when you try to set it up either as an integral dy dx or dx dy. So if we're doing dy dx, we'd be integrating y first on the inside and x on the outside. So yeah, x goes from 1 up to 5, but the bottom and the top function switch. In fact, here the bottom function is this line, and then it switches to that line, where the top is this line for a while, and then it switches to that one. So you'd actually have to break this up into 3 integrals, x from 1 to 2, from 2 to 4, and then from 4 to 5 in order to do that. Likewise, if you were going to try to do it dx dy with y on the outside, y would go from 2 to 4, but then the bounds on x change because from from y equals 1 up to y equals 2.5, you'd have this left bound and that right bound, but then the right bound switches. So from 2.5 to 3, you'd have to do this to that as the left and right bounds. And then at 3, it switches again because the left hand limit on that x integral changes to this curve then. So either way, you'd have to split that up into 3 separate integrals to do because the bounding functions are changing. So what I'm going to do is I'm going to do a substitution to see if I can get over that. And in fact, I can. Okay. Let's do this. So I'm going to rewrite each of those 4 equations. So y equals 5 minus 2x. I'm just going to bring the 2x over to the other side. So 2x plus y equals 5. Likewise here, bring the 2x over to the other side. 2x plus y equals 12.5. And then here, I'm going to do the same thing here and pull the half x over and the half x over. In this case, though, I'm going to, just to make things a little simpler, not to deal with the fractions, I'm going to multiply both sides by 2, and here both sides by 2 to end up with this. And what I notice is that these two have an expression of x and y here, 2x plus y equal to one constant, and 2x plus y equal to another constant. Those were these two edges. Right? And likewise, the other two edges, being parallel lines, could be written this way, with minus x plus 2y equals one constant, and minus x plus 2y equals another constant. And this makes me think, it makes me think only because I'd seen someone else do it. I wasn't the first clever person here. But it's like, oh, well, if we let u equal this stuff, it would turn the equation of that line into u equals 5. And likewise, the other side here would be u equals 12.5, where if I do v equals minus x plus 2y, then this would be v equals 0 and v equals 5. And so that's exactly what we're going to do. We're going to let u equal this, and v equal that, and so my 4 sides become just u is 2 different constants and v is 2 different constants. Okay. So thinking about that in the uv plane over here, so this is u versus v, where this one is x versus y. In the uv plane, this is a rectangle that runs in u direction from 5 to 12.5, and in the v direction from 0 to 5. And this transformation is going to take these UVs and turn them into those X's and Y's, and that this rectangle is going to get substantially smaller. In fact, we could figure out how small it is, because I can actually, Well, this one's easy. Over here, it's easy to find the area of this rectangle. It's, what's that, 7.5 times 5? So 7.5 is 15 halves, so 15 halves times 5. But notice over here, this is 1, this is 2, so that's the square root of 5. And this is 1.5 times the square root of 5. So the area of this rectangle would be 1.5 times 5. Well, 1.5 is 3 halves, so this is 15 halves, and this is 15 halves times 5. So this rectangle over here is 5 times as big as that one. And so the transformation that goes from here to there looks like it should be cutting the area in 1/5, right? Multiplying the areas by 1/5. Let's take a look and see now. So this substitution is not written the way I need it in order to do the Jacobian. Remember when we did like polar coordinates, for instance, we had x as a function of r and theta and y as a function of r and theta. So the x's and y's need to be written in terms here of u's and v's. So what I need to do is I need to do a little algebra and solve these two equations simultaneously for x and y. Now you may have, your favorite way of doing this. I certainly, for many years, would just say, oh, multiply the second one by 2, and then add the two equations, and the x's will cancel out, and then I'll be able to solve for y, and then do a similar thing where you multiply, say, this first one by -2 and add them up so the y's cancel out. But then it's like, I know some linear algebra. I can rewrite this as a matrix equation here, and then just multiply both sides by the inverse matrix. To get that xy is this. So this was the inverse matrix, and then multiplying the uv back in there, I get x equals 2/5 u minus 1/5 v, and y equals 1/5 u plus 2/5 v. Okay, so now I have x and y as functions of u and v, and I can find the Jacobian by looking at the partial of x with respect to u, and the partial of y with respect to u, and then the partial of x with respect to v, and the partial of y with respect to v. Right, here we go. This is how we calculate the Jacobian. Partial of x with respect to u is 2/5. Partial with y is 1/5. Minus 1/5 would be the partial of x with respect to v, and 2/5 would be the partial of y with respect to v. Notice that this is essentially just the transpose of this matrix here. Yeah, it turns out these are very closely related notions, because in linear algebra you can think of a mapping of two variables to two variables, which is done by matrix multiplication, as just a change of coordinates. And that's exactly what we're doing here, is a linear change of coordinates. Anyway, take the determinant, and I get, what's that, 4/25 plus 1/25. 1/25, and yet it says 2/25. Now it says 1/25. I had it all added up right. It's still, it should be 5/25, which is 1/5 is what it adds up to. I don't know why I had a 2 there. Anyway, so our integral, remember the integral was the integral of x plus y dA over that region. Well, that region now was, I'm doing it dv du, so dv du. So u was from 5 to 12.5, and v was from 0 to 5. The x plus y is here, right? This was the formula for x, 2/5 u minus 1/5 v, and this one was the y. The 1/5 here is the Jacobian. That is, the dx dy turns into 1/5 dv dx, right? dv du. In the uv plane, that rectangle is bigger than when you transform it into the xy plane. So you have to divide by that scale factor, and you're dividing things by a factor of 5, so multiplying by 1/5. Anyway, this now simplifies. How am I going to do this? So I'm factoring out the 1/5 from everything inside to put it together with that one to make 1/25. That constant I'm just writing out in front to multiply after integrating. And then the 2u plus u is 3u, and the minus v plus 2v is just that v. And so then we integrate v's on the inside integrate with respect to v there, plug the 5 in, plug the 0 in, then integrate with respect to u, plug the 12.5 in and the 5 in and subtract, then multiply by 1 over 25. And the volume of that integral, right? The value of that integral, which is essentially the volume underneath the surface over that region, is 49 and 3/8, 49.375. Okay. Now, when you're doing these substitutions, there's a lot of possibilities. You know, think about doing single variable substitutions, U substitutions, or trig substitutions back in Calc 2. You could do anything you want. It's just a matter of, does what you do accomplish the goal of solving the integral? Yeah, how would you even think of doing things? Well, you try some things, you see what works, you got more experience, get you better at it. Sometimes the substitution will be sort of dictated by what the function involved is, and you want to somehow change that. But as in this case, though, the real factor was the region that I was integrating over was awkward to work with. So a change of coordinate system made it really nice to work with, and it didn't really change the nature of the function at all. You know, it's not that much harder to integrate 3u plus v than it was to integrate x plus y. Right? It's just different coefficients out in front. So, yeah, you got to try a bunch of these, struggle a bit, ask questions, and start to figure out how this works. Anyway, I think I'm done. That was a really bad ending. Let's see. So there you go. There's a U substitution. No, UV sub. Yeah, this is really bad. So there you go. An integral, double integral, using a change of variables and the Jacobian.